Hi everyone, I'm Yash. So I'll be talking about probing the local environment of repeating FRBs. So in this conference till now, we all have heard wonderful talks about fast radio burst, and most of them were concentrating on the burst part of the fast radio burst. That was the most of the talks were analyzing the time series data of the burst. And that's how I also started my PhD. But later, when the field progresses, we found a persistent radio emission, where in the radio images we started seeing new things, and that's the condition of my other works right now. But yeah, moving on to the persistent radio emission. So persistent radio emission, as explained by Arvind, they are direct counterpart to FRBs, and directly probes the local environment of the FRBs. And that helps a lot because that's the only long-lived counterpart that we see for FRB. And there are very few examples of the PRS till now. So there are only a handful of examples. So for example, these three FRBs, where for the first two FRBs, the PRS that we have seen was very bright. And both of them had the spectral nature of flatter spectra. For the third one, the PRS had a little bit different spectra. It had an inverted spectra, as well as the flux density of that PRS was very low. Now the question is, are the PRS only related spatially, or is there any physics that is governing the PRS and FRB connection? So I'll be briefly introducing some of the theoretical models, how they originate the FRB, as well as how they explains the PRS origin. So one of them is pulsar wind nebula model, where the central engine is a magnetar, compact object at the center, and there is a wind nebula around it. And the theory is FRB is coming from the central engine. It can come from either rotational energy or the magnetic energy of the magnetar. And the PRS is originating from the interaction of wind nebula with the circumstellar medium. That interaction are using shocks. Then there's another model, a hypernebula model, where again there's some compact object at the center, and the FRB origin is in the jet funnel, and that's from the shocks. And the PRS origin is a little bit away from the FRB origin, and it's because of the shock interactions with the circumstellar medium. Then there's another interesting model where it's an off-axis GRB. So let's say that we're observing somewhere here, and there's a compact object which emits the GRB, and the GRB was in that direction. And the same compact object is producing FRB somehow, and that we are detecting. And the PRS, the persistent radio emission that we are seeing, is coming from is as a afterglow of the GRB event, which may not be able to detect it. Then if the compact object is inside a supernova ejecta model, a supernova shell, and again the magnetar will be giving a FRB emission, and the PRS will be from the interaction of the ejecta with CSM. Now we have some theoretical background. With this motivation, we followed a lot of repeating FRBs with UGMRT, and the famous one in this conference 2024-0114A, which was explained by a lot of people. So I'll just speed up these slides. It was discovered by Chime and then localized by Meerkat and Evian. This is the one of the bursts that we detected. You heard it in Ajay's talks. So we had monitored this burst using UGMRT in both 300 megahertz, 400 megahertz, as well as 650 megahertz, band 3 and band 4 respectively. And in band 4, we had around 10 hours of on-source time. This was spread over 4 epochs. And with that, we attempted to do imaging to look for any persistent emission. And we did detect a source in band 4. So left-hand side is band 4, which is 650 megahertz, and right-hand side is band 3 at 400 megahertz. In band 3, we did not detected any radio emission because our on-source time was low as compared to band 4. And the source that we detected was around 65 microjansky per beam. And the white circle represents the location where the FRB was detected. Now we do have a source which was like 8 sigma detection, but what we want to know is it associated spatially with FRB location or not? So for that, this is the location of the source in the image plane. First, we tried to find out the astrometric errors. So we cross-matched our detected sources with first catalog, and we estimated astrometric errors of 1 arc second and 1 arc second on both RA and deck. Our minor beam size was around 3.8 arc seconds. And this was the EVN position of the FRB. And when we cross match it, the source that we detect is within 1.2 sigma of the FRB position. So that means the emission that we see is at least spatially associated with the FRB position. Now, the emission can be also coming from the host galaxy. So to rule out that, so this FRB is residing in the satellite galaxy of a big cluster of the galaxies. And the SFR of this host galaxy is 0.06 solar masses per year. And from this SFR, if we estimate the expected flux in the 650 megahertz band, that comes out to be only 6.5% of the peak flux that we are detecting. So whatever excess flux we are detecting is probably from another objects, and that gives rise to the PRS, that points toward the PRS origin. Now we also try to model the spectra. So before us, there was a meerkat observation, and this was the same observation where they were able to localize the FRB. And I have shown that observation in red marks. This is flux versus frequency plot. Here you can also see there are faint circles. So those are the just fluxes with subbanded image measurements. And this was our observation of UGMRT. And later, there was also a 5 gigahertz observation by Bruni et al. With VLBA. And with this observation, it got also confirmed that the emission that we are seeing is from compact object. And with this, we can conclude that it's a PRS associated with FRB. And the spectra of this looks like very flat. The spectral index is minus 0.14. And if we see the subbanded structure, subbanded fluxes, we see that there is a turnover around 1 gigahertz. And later, it was confirmed by Zhang et al. That they detected a turnover at 1.6 gigahertz. So this is the first time we have seen a turnover in any PRS. Now moving on to the next FRB, it is FRB 2022-0912A. This is also followed by GMRT for a year at least. And this is one of the nice bursts that we detected. It has very good structure. And when we were following it, we did try to image it. And these are the results from the image. So this is at 650 megahertz, and we do detect a source. So we went to other bands. So there was a C-band observation. This was led by Sri Yash, and there also we detected a source of around 80 microjansky. And later there was also one more observation in band 5 by Pellissieri et al. And they also detected a source at 240 microjansky. Now we were very happy about it. But when we tried to find the spectral index, it came out to be minus 0.7, which is very close to what we expect from star forming region. And that also matches with the SFR estimations of greater than 0.1 solar masses per year. And VLBA also tried to look a compact emission, and they did not see a compact emission at 5 sigma limit of 80 microjansky. So whatever we detected is probably a host galaxy emission. Now moving on to the next FRBs. So these are the recent FRBs. It's 2023-0607A. The interesting part about this FRB is the rotation measure was very high, 12,000 radians per meter. And what we expect from the FRB PRS relation is that if the RM is high, the luminosity of the PRS should be high. So we were hoping to detect a source here. But when we tried to image both the FRBs, we did not detect a source. And these are the respective RMS, and from that we were just able to put the upper limit on the source. So this shows that FRBs have, FRB PRS pairs have different, maybe different classes where some of them only can have a PRS, or maybe all of them have a PRS and we are not able to detect it. So now to move further on with the detected PRS, we tried to put it in the context of the known progenitor models for the PRS. So there is a nice paper by Margaret et al. 2019, where they had made an analytical solution relating luminosity of the radio detected in the radio with ejecta and the energy injection rate of for the magnetar wind nebula model. So for this one of the parameters that goes is also age. And this FRB, when it was first detected by China, and after 28 days, Meerkat had detection of a continuum source. So we keep the age as 28 days. This is the fastest discovered PRS till now. And with that age, when we tried to have the constraint between energy injection and the ejecta, we got these constraint. The shaded portions, the boxes, represent the typical parameter range for supernova, long GRB, baryon neutron star, and accelerated induced collapse of white dwarf. And with the age, minimum age of 28 days, we were able to rule out these regions. And with that region, we also ruled out the possibility of accelerated induced collapse of white dwarf. One more point to note that we even tried the same thing with minimum age of 1 day, and that line also is above the AIC limits. So for this particular FRB, I think we can maybe reject the hypothesis that this is coming from AIC, but the BNS and superluminous supernova and long GRB models are still feasible. Now we also tested some of the GRB afterglow model that I explained. So what we did is we used afterglow PY package which simulates a GRB afterglow, and we tried to match the expected flux with the observed flux. And so for this, we assumed a Gaussian structure jet and with different viewing angles. So I'll just explain this plot. So this is the relation between isotropic energy of the GRB, which we may not detected it because it was off axis, and then the electron density. And the colored points are the time in days after which this emission will give rise to the luminosities that we have detected. And so these are the allowed region which are in the colored points. The dashed lines in all the plots represent the typical range of the GRBs. So from this, we can say that this model is still feasible, but it will be interesting to see how it evolved, because GRB models also, with time, it evolves, and we can detect that. There's also luminosity and RM relation, where the relation is governed by this simple formula, where luminosity is proportional to the RM, where Xi represent the fraction of electrons which are participating in the synchrotron emission. Gamma is just the Lorentz factor, and R is the radius of the plasma which is contributing to the emission. So here, so we have just put limits on this, and these dotted, dashed, and straight line shows of fiducial limits of the with this parameter range. And this was first done by Bruni et al. And what we have seen is all the PRS lies in this limit. And for the new PRS that we detected, it falls somewhere here, which is also following the same limit. And we were hoping to see something for this FRB 2023-0607A, which had a RM of 12K, but we did not detect it, any PRS there. And if we want to rule out this theory or have a new data points which is not happy with this theory, that we at least need 2 orders of magnitude deep observation to say anything. And yeah, so I'll just summarize my talk. So we detected a PRS at 650 megahertz for FRB 2024-0114A with the 8 sigma detection. And we found out there is a turnover in the spectra, potential turnover. And later it was confirmed the actual turnover at 1.6 gigahertz. And we put these results in the context of some of the theoretical models. And most of the models are in the allowed region, that they still agree with whatever our observations are. And we are only able to rule out the AIC progenitor for PRS. And for the other 3 FRBs, we for 2022-0912A, we detected a source, but it was most probably star forming region. And for these 2, we did not detect a source, and we were able to put the upper limits. Yeah, thanks. No, so in band 3, we did not had a good amount of on-source time. So band 4, we had 10 hours of on-source time, so we were able to see. But with whatever observations we had, band 3, we were not able to.
But you re-observe, right, in band 3 and see if the turnover is like low frequency also.
Oh, no, so the band 3 limit is somewhere here. So one of the problem with the band 3 observation is also there is a bright source between full width half maxima of the beam and the deconvolution errors becomes very high. So that's why we are also not getting very good RMS.
Yeah, so can you go a slide, next slide? I think, no, the place where you showed different models as per the, yeah, this one. So the lines of for the ruled out, the boundary of the ruled out and non-ruled out, what were the data points? As in, were they on the both sides of the line or just one side? So how did you had these lines?
So there is a relation with luminosity, or that is the detected observable point between ejecta and energy injection, and time, the age of the PRS, and all other parameters we assume in some range where it's possible. And then just based on the age, the age must be greater than 28 days, the line will be somewhere here.
What's the age? What is this minimum age?
So
mean?
So here we have put the minimum age as when the FRB was first discovered by Chen, that's the first detection, and when the first continuum emission was observed. So we took that as the minimum age of the PRS. It can be more than that, but we know for sure that the minimum age is 28 days. So that's how we have a allowed region where the age can be anything more than 28 days. And that's how we ruled out this region.
So in one of the slides, you mentioned that the star formation rate based luminosity estimate was lower than whatever was detected, and therefore you were able to rule out star formation. Do you worry about the fact that this star formation estimate is a global estimate, basically coming from the full galaxy as opposed to just the local region of the FRB itself? And is there any way you could account for that?
That can always happen, that the global star formation rate is slightly lower than the local, and local has a very high star formation rate. But in case of this FRB, with the VLBI observations, you can confirm the compactness of the source, which was less than 0.7 parsec. So that gives more confidence. And also the spectra that we are seeing, it's almost flat. So that is one more thing. And also, since this was a satellite galaxy, the star formation rate for the central galaxy was much higher from this. And in the radio image, if we compare the location, the central galaxy's flux is much lesser than whatever we have detected here.
Yeah, just a quick comment that I think one of the useful ways to separate between some of the existing models for PRSs would be to actually have observations going beyond the gigahertz range. So either at high frequencies or lower frequencies, we expect to see turnovers of the spectrum. And especially the cooling break is directly indicative of the age. So if we have that, it will really help to disentangle some of what is going on here physically.
Yeah. Also for the cooling break, but the frequencies are like in the ALMA frequency range. And
it depends a lot on the model. Yeah, they can be anywhere between 10 gigahertz and orders of magnitude above that.
Okay. So for this particular FRB, we also followed it with VLA, and we have, I think, detection till 10 gigahertz, and that looks flatter.
Yeah, so that's very useful.
Okay, so let's thank Yash and all other speakers in the session.